Now, let's take a look at the first queuing example. Western Bank has a drive-through window for customer service. Management estimates that the customer will arrive at the rate of 15 per hour. The teller who will staff the window can serve customer at a rate of 1 every 3 minutes, assuming we have person arrival and the exponential service time. We want to find the utilization rate, the waiting time, and the number of cars in line, something like that. So how can we solve this problem? So first, we notice that the arrival rate will be 15 and it will be the person arrival, and the service rate will follow the exponential service time. So basically, we know this is M and 1Q. Remember, the first M stands for the person arrival. Second M will be the exponential service time. The third letter, number 1, means that we only have one server. And when we try to solve this type of problem, the first thing we want to do is to realize what will be the utilization rate. And we know the arrival rate can be denoted by lambda. In this case, lambda will be 15 per hours. But if you read the problem carefully, you will notice that everything will be described in minutes. So the first thing we want to do is to convert this to minute. So I have a quarter arrival per minute. Okay? And we also see that the service time will be 1 every 3 minutes. So every 3 minutes, I will be able to serve one customer. So we don't have service rate here, we have service time. Service time will be 1 over mu. And this one is equal to 3. Okay? And in other words, our service rate, mu, will be 1/3 per minute. So I will be able to serve 1/3 of customer every minute. So once you know lambda and mu, we can figure out the utilization rate. And we call utilization rate rho. Rho will be equal to lambda divided by mu. In this case, we have 1 over 4 times 3, which means the utilization rate will be 0.75. So on average, the server will be busy at 75% of the time. Okay, so when you go to these locations and the probability of 7.75, you will find that the server will be busy. The remaining 25%, you will realize that the server is not busy, so you don't have to wait. And the first thing we want to calculate here is the average waiting time in line. And remember the formulations for that. The waiting time in line means we want to calculate WQ. Q means the queue, so WQ will be the waiting time in line. And since we have MN1Q, the formulations is actually equal to rho divided by 1 minus rho times 1 over mu. You can find the formulation on the previous slide. Okay, so we just plug in all the numbers. 0.75 divided by 0.25 times 1 over mu, which is 3, and the answer is equal to 9. And the unit will be minutes. So your average waiting time in line will be 9 minutes. Once we know the number, the waiting time in queue, we can also calculate the number of cars in line. So remember, if we want to calculate that, we want to find out LQ. LQ, the number of person or the number of car in line. And we can use the Little's law. So LQ will be equal to lambda times WQ. In this case, it will be a quarters times 9. So I have 2.25. The unit is cars. Okay. If you knew WQ, you can also calculate the average waiting time in the system. and we call this WS. And based on the formulation on the previous slide, we know WS will be equal to WQ plus 1 over mu. This makes sense because your average waiting time in the system will be your average waiting time in the line plus your average time you get served by the server. So in this case, I have 9 plus 3, which is 12. The unit is minutes. Once you know WS, you can calculate LS, the average number of cars in the system. And again, you apply the Little's law. I know LS is equal to lambda times WS. So in this case, it will be a quarter times 12. That will be 3. So on average, there will be 3 cars at these locations. Finally, for the MN1Q, we can also calculate the probability of having a certain number of cars in the system. So if we want to find the probability of having less than 3 cars in the system, basically we want to find out, let me write down the formulation first. So we denote Pn equal to 1 minus rho times rho of power of n, and Pn will be the probability that you have n cars in the system. So in this case, we actually want to calculate P0 plus P1 plus P2, because the probability of having less than 3 cars in the system means that the probability of having 0 car plus the probability of having 1 car plus probability of having 2 cars. Okay, then you just plug in all the formulations. This is equal to 1 subtracted by rho times rho of power of 0 plus 1 subtracted by rho times rho power of 1 plus 1 subtracted by rho times rho of power of 2. Okay, so everything here will be equal to 1 subtracted by rho times rho 0 plus rho power of 1 plus rho power of 2. Then you just plug in the number. This is equal to a quarter times 1 plus 3 over 4 plus 9 over 16. That should be equal to 0.5781. And that will be the final answers.